Good morning, chemistry people! Welcome back to another edition of Chemistry Learning. Oh yeah, today we are going to Today we are going to begin actually diving into like what makes a battery. What is how do batteries do? So what we had to start with is first we had to identify what a redox reaction is, because you can't really know about redox reactions if you don't know what a redox reaction is. So let's start there, right? The next thing we did is we talked about oxidation number, and we learned a little bit on how to find oxidation number, because if you can't find the oxidation number, how are you going to even know what's going on, where are electrons going, and all that kind of good stuff, who's gaining, who's losing, which is really important when you're having a battery, which is like making electricity. And then we went in and then we did half reactions, and that was like the very beginning, where we basically looked at just the oxidation or just the reduction, and that was super important, because as you'll see moving forward, this is the first step to splitting a battery apart to the positive end and the negative end, because we all know the battery has a positive end and a negative end, so that electricity happens. So what we're going to do today is continue all of that learning into electrolytic cells and stuff, electrolytic Voltaic and all that kind of great stuff. It's going to be awesome. It's basically battery time. I hope you guys got out and enjoyed the weekend. Man, it was spectacular. I don't know about you guys. I had a great weekend because, the sun. And now we're going to talk about this, electrochemistry. Let me choose a Viking red as usual. Electrochemistry, first thing, all right, look. Some of these words, I know that science has really weird words, but sometimes the words we try to keep it really simple. Guess what an electrochemical cell is? Do you see the two the prefix, the two parts of the word here? Can you imagine what an electrochemical cell is? Basically, it's an apparatus or a thing. Apparatus is a fancy word for thing that uses a redox reaction and a flow of electrons to do work. Something. It doesn't necessarily have to be a battery either to do something. It could be making electricity. That's the one that we know most often, which is like a battery. We could be recharging a battery. I mean, that's using electricity to do work. The work that we're doing is recharging the battery, you know what I mean, that went dead from the other day. So yeah, there's that. There's also electroplating. There's electrolysis. There's specifically hydrolysis. That's splitting. Electrolysis is when you take a compound and you break it apart into its elemental components, but specifically hydrolysis is when you split apart water into its elements. It's really important because it's water, you know what I mean? So for us, there are only two kinds of electrochemical cells that we will be dealing with. Got it? First one, this is the one that most people know about and are aware of, the Voltaic cell. Now look, Voltaic. See how there's a volt thing there? That means that this thing is going to produce voltage. It's basically a battery, man. Hey, man. So it's an so a Voltaic cell is, specifically speaking, an electrochemical cell that converts chemical energy to electric energy, to it says right there, electricity, by using a spontaneous redox reaction. Now this part right here, this word it has to be spontaneous, okay? In other words, it has to happen all on its own, because that's how you want batteries to work, right? You pop a battery in your thingamajiggy and your thingamajiggy turns on. That's what we mean by spontaneous. In other words, you don't have to do anything weird to make it happen. It just goes. So yeah, this Voltaic cell, it is basically, you and I have come to know these things as batteries, because that's what they are. A Voltaic cell is a battery. Now, this is the part that is not super common knowledge, is that we're starting with chemical energy, stored chemical energy. We're starting with stored chemical energy, and that chemical energy is turned into electricity. You guys dig what I'm saying? Sweet. Now, the next one that we're going to look at, not today. Today we're sticking just with the Voltaic. Now this one, the electrolytic cell, here's the thing. This one, this still uses electric power to cause a non-spontaneous redox reaction to occur. Okay? So this is using an outside energy source. So, outside, electric power, outside source. This is super important. it is very important for you to lock in that this is an outside power source. Is it SE? I don't know. SC, who cares? Tomato, tomato. So an electrolytic cell would be like, here's the thing. It's all about like the setup. If you have your cell phone, right, and you're using your cell phone, that battery at that moment is a voltaic cell, right? Battery goes dead. What do? You plug it into the power grid, which is like a lot of electric power, right? And that uses that is using an outside power source, right? It's going to be whatever generation source we have. Turbines, water. Dear God, I hope we don't have any coal idiot firing burn plants. But anyway, it's an outside power source that is going to force the electrons in your cell phone battery to go backwards, right? So like spontaneous happens all by itself. A non-spontaneous requires an outside power source to force the electrons to go in a direction that they normally wouldn't go on their own. Does that make sense? I certainly hope so. Basically, anything with an outside power source, anything that uses a battery to do something, that uses a battery to make a redox happen. So in our homeworks and stuff, anytime you see a battery, it's that right there, instantly electrochemical cell. Got it? So again, the voltaic cell produces voltage, right? The voltaic cell, this is a battery. The electrolytic cell uses a battery to make a redox reaction happen, to force it to happen. We use this a lot with like electroplating, recharging batteries. Submarines use it to like do hydrolysis to get oxygen out of the water. There's a lot of uses for this stuff. We don't usually see it or recognize it in our everyday, but anytime you recharge a battery, you are producing an electrolytic cell. Got it? Great. Good. Today we're going to stick with the voltaic cell. So here's the situation for voltaic cells. What color you want to do today? Let's do this color. All right, so here is our chemical equation, right? And this is a really common one because it's easy, it's nice. It's one of the first ones. I think they used nickel and copper for like one of the very first batteries. But anyway, zinc is a nice metal. It's harmless. Copper, pretty harmless. And this is our basic, like, of course, there's going to be other things. Copper is probably going to be bonded to something. Zinc will be bonded to something, but we don't care. This is where the action is happening. And if you look, the zinc starts out as a 0, and it turns into a 2+, so it's going to lose 2 electrons, and the copper is going to go from a 2+ to a 0. So this one here is going to lose. This one's here going to gain, right? So if zinc is losing and the copper is gaining, let's go through this. 2 electrons move from copper to zinc. Excellent. Redox. Check. We have a check mark there. This is a redox reaction. We can make a battery out of this. Now, the electron transfers happen spontaneously, in other words, all by itself, if the electrons go from higher on table J to lower on table J. So what we need to do is we need to go to table J, write that big, long list of elements and whatnot, and we have to look for zinc, and we have to look for copper. And if it is zinc up top and copper down low, and the electrons drop like this, that means it'll happen spontaneously. In other words, if we set this up as a battery, it'll just start working like a battery, making electricity. Let me go check table J. Yep, sure enough. Turns out zinc over there is going to be higher than copper on table J. So this will happen spontaneously. That is spectacular. So yeah, there you go. So what happens is our oxidation is right here, right, where zinc loses 2 electrons. If you notice what's going on there, right? There's the electrons. They popped out, right? And over here, it's reduction. It's gaining electrons. The electrons are going to be smashed right into that ion there, right? And it's going to turn copper ion into copper metal, right? So this is a really important part to like dial in here. This is zinc metal. This is literally a hunk of zinc that is turning into zinc ions that are going to be dissolved in solution. And exact same thing, only completely opposite over there is where copper is going from an ion, right? From an ion dissolved in water. it's going to turn into copper metal. And that's what's happening inside batteries. One is an ion turning into a metal, and then there's a metal turning into an ion, and then vice versa. And if we can take these two things, right, like what we have right here, if we can just somehow separate these things so that they happen inside different containers, right, and then put like a battery or something like a wire, right, so that this end of the wire is connected to this reaction and this end of the wire is connected to that reaction, we will have electrons zinging through this thing. Does that make sense? And that is exactly what we did with battery. That's exactly what we did with battery. Believe me, it didn't happen like this brilliant way. They just realized something weird was happening, and they're like, what's this weird thing happening? And then they realized later on. But that's basically the idea of a battery. So why did we learn half reactions? Because a half reaction is half of a redox reaction, and it turns out it's also half of a battery. You have to have one half over here and one half over here. You guys get what I'm saying? So if we do separate the half reactions, we can make them move through a wire and do stuff like, I don't know, make your little whatever dilly-woppy thingies work, make a light bulb light, make a computer compute and stuff like that. So, but let's start with the very, very beginnings now. What we're going to do here is we're going to look through the anatomy of a voltaic cell, the shape, the parts, the pieces. And this is what batteries look like back in like the Victorian ages. They actually had like doorbells made out of this stuff, and it is exactly like this ridiculous thing that you're about to see. And it actually worked. It worked pretty well, except like right above your front door, you'd have like a box full of toxic chemicals. But whatever, they had a great doorbell. And every single one of these things that we're going to learn about now still exist in every single battery there is today. So every modern battery has one of these pieces and parts. Now, granted, they don't look exactly the same, but they do the exact same function. They are obviously more advanced, more weird, more engineered, more efficient instead of what we're going to see. But every battery has all of these things. Like even your Tesla cars, those brand new batteries have every bit and piece that we're going to learn still in batteries today because you have to have them. So here is our voltaic cell. Isn't it beautiful? Yeah, right? So here's what we got to have. We need one beaker, two beakers, and we have to have this thing, right? And then why don't we just go ahead and start labeling stuff today? This is going to what we call a salt bridge, and I'll explain that in a minute. So this is a salt bridge. This is a hunk of metal. This is zinc. And then this right here is a wire. And then this is a thing. Here's your wire. And then this is a chunk of metal. Oops. Sorry. All right, so got it? So here's the setup. In this beaker over here, I'm going to need some kind of ions that are zinc. So I need a bunch of zinc ions in here. So whatever solution you need, as long as there are zinc ions in here. Okay? So it's a beaker full of zinc ions and a chunk of zinc metal connected to a wire. And in between the wire, we have this thingamajiggy, whatever it is, I don't care, a lamp, I don't know what that thing is there. But anyway, that thing. Then it comes over here to a big hunk of copper. Now, over here, I'm going to need... let me see if I can fix this here. No, I don't think I'm going to fix anything. So, what's important is that we have a bunch of copper ions in here. You got it? Okay. So, we have two half cells, so we have the whole thing. We have a hunk of one metal connected by a wire to a hunk of another metal. Whatever metal we have over here, we need to have those ions in solution, and whatever metal we have over here, we need to have those in solution. And then there comes this thing, a salt bridge. So here's what happens. This salt bridge is basically, it's literally in the original batteries, like what we're calling, this is called a wet cell battery because it's full of solutions and you can spill it because it's wet. Electrons are going to flow And so nature doesn't allow things to become unbalanced. It just doesn't. So what we needed to have is this thing called a salt bridge, which is literally just like a bent tube like this, typically made out of salt. And right here, there's like a plug. You see that little plug down there? Yeah, that guy right there. So this is like a plug, but it's porous. What's often used in labs is we'll take a piece of cotton and we just dip it into a salty solution, and then we pop it up in there so there's just like a cottony plug right there. And now inside here, we have salt water. So I don't know what kind of salt you want to use. Let's use sodium hydroxide or sodium chloride. All right, so there's like salt all up in here. Oh, here's the little plug over here. Salt, 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 salt. And what it is salt is actually an electrolyte, which allows charge to move and travel. So all of this thing here, like there's salt all up inside here, but remember it's like a salt water. And so what happens is as the electrons are moving around, if they go from like one side to the other, it's going to make an imbalance in charge. So what happens is this salt bridge is here so that ions can flow in order to balance charge. You want to so here's what happens. So there's the anatomy. Let me double check. Big hunk of metal with the ions, a wire, a thingy, a different metal, beaker full of similar ions, and a salt bridge. That's all you need. Great. Here is what happens. We're gonna go to table J and we're gonna check out our metals here, right? And just like we had from before, zinc is very high, copper is very low, so the electrons are going to flow downhill. This will happen by itself. This will happen spontaneously. So here's what happens. A wire is basically plumbing for electrons. It's a tube through which electrons can flow. If you think of electricity like plumbing, they work surprisingly similar. So what happens is, because copper is lower, it is pulling on electrons really strong. It has a greater electronegativity than does the zinc. So what happens is the electrons leave zinc, they like physically leave the zinc metal. They're going to go through the wire, and as they're being pulled through the wire, they're going to go do work through your like whatever thingy that is, and then they're going to come over here into this copper. So here's what happens on those electrodes. Because copper is lower on table J, it is going to be pulling electrons towards itself. How? Because it's connected by like this like electron conduit. So what happens here is let's do this one electron at a time. One electron is, or actually, let's do two because these are 2 pluses. My bad. So 2 electrons are ripped out of this zinc. So what happens is a little piece of zinc, a zinc atom, loses 2 electrons, and it becomes a zinc ion, right? So these 2 electrons, they go up the wire. Oh, in this dotted line, and so this is electron flow. And we know that electron flow is going to go this way because copper is lower is lower on table J, right? So it's like the copper is pulling the electrons towards itself. So again, these 2 electrons, like this zinc loses 2 electrons, it turns into a zinc ion. These 2 electrons go zinging through the wire. When it gets to your thing, it does stuff like, I don't know, makes the animals cross on your cell phone. I don't know, whatever you guys are doing with cell phones. Whatever games there are. So the electrons come in here and bam, they get smashed into this thing, right? So here are our 2 little electrons now residing inside the copper. Well, look, guys, look at this. You got over here, you've got like a plus thing, or I'm sorry, it's like 2 extra electrons, and look at the charge of those ions, y'all. Y'all see that? Right? Isn't that a thing? So you have a positive thing and you have 2 extra electrons over here. What happens when there's a positive thing and a negative thing? You bet, man. They are attracted to each other. And so what happens is a copper ion is attracted to these 2 electrons, and then it gobbles up those 2 electrons and goes from copper 2 plus to copper 0 and turns into bloop, a little blop on top of that electrode. And so it continues. Two more electrons come over here. Another little piece of zinc is like dissolved out. This comes into solution. The electrons go through the wire. They do more whatever work you want them to do. They come into here. You get two more extra electrons. Those two extra electrons attract another copper ion, and bloop, it turns into a blob of copper, and so on and so forth, until over here you eat away, and this eats away, and this eats away, and this eats away, and then it starts eating away over here, and then over here, until one of two things is going to happen. Either you're going to dissolve this electrode completely away, or every last copper ion turns into a chunk of copper metal on your electrode, and you have an electrode covered in brand new copper ions, and you run out of ions. And then your battery's dead. Voila. That's it. Now, if it's a well-engineered battery, turn into an electrolytic cell and reverse the flow. But we're not going to go there just yet. But do you see how what you could do is, instead of having a thing here, what if you had an electron pump that shoved the electrons that way? Right? It just forced them that way. How would you force electrons to move? You plug it in to the power grid. I'll make any electron. I'll make any number of electrons move. That's a ridiculously huge amount of power in those power lines. So it just shoves electrons the other way, and it reverses the order of operations. We will look at that later. Let's look at what's happening down here, guys. Right? Over here on this side is where oxidation has happened. We have literally split the half reactions so that the oxidation happens here. The zinc atoms are losing electrons and turning into zinc ions, and like spitting out two electrons, right? These two electrons, out they go. Now over here on the other side, this copper, these two electrons are crashing into that copper, and it's turning it into a copper metal. And in between, we have a wire, and it does work. You guys get what I'm saying? Isn't that amazing? However, I didn't talk about this thing here, did I? So what happens? Do you see how over here we're gathering a whole lot of pluses? And over here we're losing all the pluses, and all the electrons are building up over here. Man, we can't have electrons down here and too much positive like over there. It's not, no, man, you can't put positive charge over there, negative charge over there. That's like unbalanced and unstable, so nature will not allow that to happen. So what does happen is this salt bridge, we say, allows ions to flow to balance charge. So as this side over here, right, as this side becomes way more and more like positive, we're going to get an inflow of chlorine ions are going to flow into here to balance the charge. And over here, we will have an influx of sodium ions. Why? To balance the charge. You dig what I'm saying? So if any of these things run out, if we run out of salt in our salt bridge, if we dissolve away our entire chunk here of metal on the oxidation side, it stops. If we lose all of our ions over here on this side by this big chunk of metal, it stops. You got it? Oh, hey, that's a thing. A bit of a detail here. There's kind of a problem. We've got this container thingy here, and this container thingy here, and this chunk of metal thingy here, and this chunk of metal thingy here. That's not going to work out. We can't call them thingies. It's not scientific enough, and we don't sound very smart. But what we can do is give them fancy science words. So what do you think you should call the cell, which is being sciencey for container? What do you think we should call the cell where a half reaction happens? You know, like where half the redox reaction happens. You know, in that cell. That is one half cell. This is the other half cell. Okay, you guys get what I'm saying? Awesome. So a half cell is where one half of a redox reaction happens, either the oxidation or the reduction. Salt bridge allows ion flow to balance charge. Big metal hunk of thing. Man, we can't call it big metal hunk of thing. We have to come up with a good scientific name. So this has a name. It's called an electrode. And this is also an electrode. Big hunk of metal where either oxidation or reduction happens, but the problem is you can't call them both electrodes because you can't. I think it's just you can't call two things the same name. Like, what are they? They are electrodes, but there are two different categories of electrodes. So here, what is happening here? We are losing electrons, so this is going to be an anode, and this one will be a cathode. This is the cathode. Why? Because the cations, positively charged ions, are attracted to it. That's why they came up with it, because they didn't know what the heck was going on, man. They just plunked it into the water, and you're like, dude, that is weird. They're like, what's going on? All the positive ions are being attracted to it. This electrode thing here. So like, well, we should call that the cathode. And look what's happening with the other electrode. And they're like, whoa, all the anions are attracted to this one. Anytime we put anions in there, all the anions are attracted to it. Let's call it the anode. That's it. That's why. So electrode, specifically this one's the anode because it's where oxidation is happening, and this is a cathode because it's where reduction is happening. But these are both electrodes. Salt bridge, wire. I think that's about it. You guys want to move on? Two things before we go. Electrons flow towards the electrode lowest on table J. That's how you determine electron flow. Why do you care about electron flow? Well, if you put a battery in backwards, nothing happens, right? You got to have flow the right way. I mean, look, see? Like, you got to have flow. How could you get by without flow? Not really. It's like literally making sure that your battery is like put in the right direction, so you know like what direction the electrons are going in the circuit, so you can make it work properly. And the other thing that we really need to keep in mind is that the ions in the salt bridge flow in the direction which will balance charge. That is the whole point. That's weird. That is the whole point of a salt bridge, is to balance charge so that this can continue to flow. Oh, I guess that's why that happened. Let's draw this in here for you. Words. So many words. Dude, guys, we got so many words. We have the best words. There are so many. We know all the best words. Our words are the best. We have words you don't even know. They're so good. Most people don't know them, but I do. There's such good words. They're the best words. Most people don't know. Okay, man. Half cell. Like I said before, these are separate containers where one half reaction occurs. It's where either your oxidation or your reduction happens. Right? Easy. Salt bridge. I think we covered that pretty good. It's the pathway that allows ions to flow between half cells to balance charge. That's the point of the salt bridge. Now, the electrode, we didn't really formally, it's like a hunk of metal, but yes, the site. We don't want to say a hunk of metal because it doesn't necessarily have to be metal, but this is where oxidation or reduction occurs inside the half cell. Okay? All right? So it's important to know it doesn't always have to be metal, because modern batteries don't actually use metal for both electrodes. Now, we do have to have this dialed in, whether it is a cathode or an anode. So, cathode is where reduction happens. Oops. Oop, there you go. That is weird. And an anode is where oxidation occurs. You have to have that memorized. You got to have it memorized. And you might ask yourself, whoa, you might ask yourself, how am I supposed to remember? How am I supposed to remember what is happening at each electrode? It's a good question. It's a legit question. It's something that you should learn, and you should have it dialed in your brain. Why? It's no longer for the Regents anymore, people. But really, if you're going to leave here, so I guess this is my motivation thing, is like, if you're going to leave here and ever have any hope of like going to college and surviving your first year, you want this. Because this is the stuff that, like, it's just good to have it now, so it's not brand new when you move on after this crazy time we're in. So how are we supposed to remember what's happening at each electrode? Like this. Follow along and draw. And I'm going to tell you right now. People, man. So many people did not include Leo in their last drawing. And I can't. I cannot express to you the sadness that settled into my bones when I didn't see any Leo. It's like the notes are just so sad and lonely without this fluffy, fat lion guy. You better put him in this time. Just follow along. Get your digital pen. Let's do this. All right. Draw a triangle. Boop. And then draw another triangle. And draw another triangle. And a line inside the triangle. Just like that. Then right here inside your triangle, go bloop, 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 bloop. Just like that. What could this possibly be? I don't know. So see how this is a triangle? I'm going to continue this triangle for a right side up triangle. And inside the triangle, I'm going to draw a number 2 and a line. And another little line. And then I'm going to go like this. That is so cool. I'm going to add a pen. Let's see what color we can do. Let's do more colors. This is going to have to be a... Ooh, oh, yeah. Okay. Yep. That's the one. All right, now over here, we're going to go like this. We need yet another thing like that. I'm going to have to edit these. But this one, you don't want a triangle. Nope. No triangles. It's got to go like this. And then these guys go down here. And then like that. Then like that. Then like that. And like that. Then like that. Okay, all right, so are you that far? Awesome. Now that you have your little triangle with horns and ears that drop down, you need to make a box that goes like this. Big old box. And then a line and a line and a line. And then do a line and a line and a line. And then go bloop, bloop. Give her some hooves. Give her some, oh, I hinted it. There you go. And then, of course, this one's tail is going to go like this. Maybe we'll give her him. I don't know what it is. A little blotch it up here. What do you think? A little blotch in the back. A little blotch right here. A blotch. There. Isn't that awesome? Look, we drew stuff today. This is spectacular, man. We're killing it. What is this? This is a red cat. Red cat. That's an ox. Can I see? See how it's a red cat. That's an ox. That's great. I mean, I love that. Come on, that's great. Red cat. Oh, wait a minute. 5 pillars of knowledge. Leo, says Gurr, electrons roll downhill. Red cat and ox. You have everything you need to know to be wildly successful in this chapter. Red cat. Red cat. Reduction happens at the cathode. And ox. Anode is where you have oxidation. Man, that is like genius. All the hard stuff. Rememorize. Leo, says Gurr, electrons roll downhill. Red cat and ox. Genius. Genius stuff here, people. Maybe I'll stay here. Do I have more to do? No, we don't. Look here. Look at this. I didn't even realize it was the end. We're done. Well, for today. We're done for today. 2 homeworks. Applying activity series. That, I want you to listen to me here for this one. There's going to be a bunch of it should be really quick, like 5 minutes at most. Get out Table J. Check it out. All I want you to do is say yes, no. Will this react? Will this be spontaneous? Will it not be spontaneous? And here's the clue. On the reactant side, the metal, whatever metal it is, that's the one that's going to be losing the electron. And on the reactant side, whatever the metal ion is, that's the one that's supposed to be receiving the electrons or gaining the electrons. And if you remember, they have to go downhill. So, to have a spontaneous reaction, the metal element has to be higher on Table J, and the ion has to be lower on Table J for it to happen spontaneously. Do you guys understand what I'm saying? Sweet. The next thing is Chapter 9, homework number 4, Voltaic cells. You know how to do these ones. It's a homework. Just do the homework. It's a homework, so just do that. Okay? You guys, thanks for sticking with me the whole time. I hope you guys are enjoying your time at home. Also, just so you know, we are rapidly approaching the end of the chapter. Or, I'm sorry, yes, the end of the chapter, and then the end of the year. We have one more to go to wrap up this chapter. Like one more video lesson thingy. And then after that, we have organic chemistry and nuclear chemistry, and then we're done for the year. So it is coming quick, my friends. So good or bad, there it is. That's what's happening. I hope you all have an awesome day, and I will see you very soon. Toodaloo.